the importance of backups. All right, welcome to week 6. So thank you for submitting your assessments. So we just have to wait out the week because technically um, there's like a maximum of 1 week allotted time that people can apply for extension. So we can't really start evaluating them until the end of the week. But I will provide you some solutions to the assessment on Friday when we deploy A2. Something I should mention about A2, the deadline for that's also been pushed back by 1 week. I hadn't done that originally, but then I was like, I did it anyway. So it's the jack's already been changed. So do amend your calendars. The assessment 2 is actually due after the reading week now. Any concerns or questions before we move on about course structure? No, I should be a little bit more energetic because my module teaching in 1001 ends this week. So I'll be able to give you guys a little bit more focus moving on from now, which is great because that class is just sucking the life out of me. Okay. This one's fun though. Okay, so what we're going to talk about today is higher order functions and then more about algebraic data types, specifically the product types. And we're going to, for the first time, define some custom instances. But this lecture on higher order functions is pretty important because these are these are going to be the higher order patterns that we should mostly be programming in, generally speaking. And then these are all the patterns that we're going to, from this point on, keep generalizing until the end of term, until we eventually generalize so far that we have monads and reintroduce sequencing back into our functional paradigm. So let's get that going. So what's a higher ordered pattern? Strictly speaking, a higher ordered function is any function that maps functions to functions. Now, like this is effectively everything in Haskell and to some extent Python as well. So in practice, what we mean by a higher order function is a function that merely accepts functions as arguments, right? It may return a function back or not, but the key thing is that it's a function that takes a function as input. And this is something that's set up in Haskell to do naturally. Python actually treats functions as first-class objects, which is important. Like in a language like C, how easy it is to pass a function to another function. Is it possible? Yes, it's possible. Anything's possible when you have pointers, right? You just say it's here in memory. But it's certainly not set up to do so nicely. So the first higher order pattern that we're going to talk about is map. No, she hated the lecture already. Okay. She is map, and this is a way for us to make a structure preserving transformation on some type of object. And what do I mean by this? If you have a list, any change that I can make to that list that makes the list length remain invariant qualifies as a structure preserving map. Like for example, so you have this function, higher order function map. It takes a function which goes from A to B, and you give it a list of A, and you give it a list, and you get back a list of B. So for example, I can do something like map 2 times to the list 1 through 10, and out comes 2, 4, 6, 8, all the way to 20, right? So nothing about the shape of this list has changed. It has the exact same structure. It's of the same length. But the things inside have changed, right? So this is why we call this a structure preserving operation. And this is something we're going to generalize a lot. The nice things about these maps are that they will continue working on streams, right? So I can say X is map 2 times to the infinite list, and we're still free to take members out of that, right? So like you can map over things that are totally infinite because if we work out what map does, like, so for example, if we wanted to program it, I'll just do it. I'll create a new one. Am I on the desktop? Yes. Sandbox. We'll just program it Haskell. Module sandbox where, and let's just define map, but I'll call it map like this, right? So we can define this. So map is something that takes a function from A to B and a list with A and a list to B. And we can just start programming this. So what was our philosophy? So we have to designate the edge cases. So certainly we have to be concerned about what happens when we get the empty list. Once we're concerned about what happens with the empty list, then we're free to do a pattern match like this. So what do you suppose we should return when we map something over the empty list? Sounds fine to me. Yeah. And what do you suppose we should return if we map f to x cons x's? Exactly. So we take f, we map it to the head of the list, and then to the remainder of the list, we just recurse, right? So we want to map prime f to the remainder of the list, right? So because we're just doing this, you can see how this is going to sort of allow us to have infinite streams, right? Because we're just taking off the head and doing something with it and recursing on the tail, right? So we're not actually mapping along the whole list. You're only mapping that list once you want a list element from that list. I'm going to show you how map works just by sort of defining this weird function, which is just going to decorate a number, right? So I just defined decorate, and you want to give it 1, and it's just going to show f of 1. So if I take map and I just decorate over this list, what you're going to see is sort of the generalized pattern, right? You're just going into that list and you're applying f to every member of that list. Most of you are familiar with maps already. Yeah, once you get a list comprehension, you effectively get a map. So we can define map sort of with a list comprehension to say, just look at your x's and draw from x's, and then just sort of take f and sort of send x through f, right? That's going to be a sufficient definition for the map. Is this better or worse than this one? So is this going to work with streams? Let's check, because if it doesn't, then it's going to be worse. So let's see. If we have y's, and I want to say sort of take 2 times and apply it to x such that x is drawn from 1 onward. Can I do this? Cool. So it seems like either one is fine in this case. So any language that has list comprehension, you can effectively have a map, right? So Python has list comprehension, so you kind of have a map. Although you have to be careful in Python because list comprehensions don't give you streams; they're not delayed. But here you go. So we can always define this using a list comprehension and using recursion. So map, that's sort of maybe the easiest high ordered pattern. We also have zips. Is anyone familiar with a zip? Yeah, so this is more sort of when you take 2 lists, and from those 2 lists, you want to produce tuples. So give me a list of type A, give me a list of type B, and I'm going to give you back a list of tuples of A and B, and look something like this. So if I zip 1, 2, 3 with 4, 5, 6, you're going to get a list of tuples 1, 4, 2, 5, 3, 6. Now, what do you suppose happens if one of the lists is longer than the other list? Yeah, well, maybe stop at the smaller list. So what was another option? Empty list is the first argument. Oh, you want me to put an empty list in for A? That wouldn't type properly though. Yeah. The answer I'm looking for is we could have picked some type of default padding value if we wanted, right? Absent of we could have said just use zeros, but that's not the case. So this just gives you 1, 4, 2, 5, 3, 6. How about this one? It's going to truncate to the shorter list, which is on the right. So we're going to get -2, 4, -1, 5, 0, 6. So far, nothing too complicated. Can we define zip? That should be a fun exercise. So zip prime, we have list of A, list of B, and we want to go to tuple AB. How can we define this? Well, we got to sort of work through our baggage. So there's baggage if the first list is empty. There's baggage if the second list is empty. What should we do when one of the lists is empty? Yeah, I don't think there's any tuples to produce, so we can do this. What's if neither of the lists are empty? Then I can do these 2 pattern matches. Can I not? That's safe. That's fine. So if I can grab those 2 elements out of zip, then this is going to be something like, give me the tuple xy, and then connect with the recursion. You are correct. Thank you. Here. Okay, let's try zip prime. 1, 2, 3. And 4, 5, 6, 7. Whoops. Is zip prime already defined? Did I not? Oh, I'm loading the wrong module. That should be better. Zip prime. 1, 2, 3, 4, 5, 6, 7. There you go. I was not too bad either. Okay. Zip width. This one's a little bit more useful. It has a type signature like this. So basically it does everything that zip does, but you also give it a bivariate function. and then you give that tuple to that bivariate function, it actually gets evaluated. So it's something like if you want to zip with plus along these two lists, what this is effectively going to do is give you the pointwise addition between those two lists. So this is quite useful. You get 5, 7, 9. What about zip with one of the lists is longer? What do you suppose happens here? We're just going to truncate to the shorter one. Same with the other one. Okay, cool. I know I'm going through these quite fast because the pattern I care about most is fold, and that's going to require most of our attention. But this is a good warm up. How can I? Let's take this and let's make this a zip with, and we'll just have to modify this a little bit. So we have to have a function argument here. What was the function argument? Takes A and B and goes to C, and that's going to give us a list of C. So I guess here I don't care about the function because it's an empty list. I also don't care about the function here because there's an empty list, but I do care about the function here. And I suppose then I just do this. Yeah. That's... Oh, yes. One more F here. Okay, let's see if that works. So can I zip with prime? Let's just say multiplication. 1, 2, 3, 4, 5, 6. Hooray. Right, so these are pretty useful, especially when you tie them together in function pipelines, but let's keep going. Okay, so that's how we can filter. Okay, so filter is used to select members of a list that satisfy some predicate. So it looks like this. You give me a predicate, anything that takes A to bool, then a list of A, then I give you back a list of A. This always drives me crazy. What do you think filter, if I filter the evens from this list, what's it going to give back? And I always reverse this somehow. So you suppose that this is a predicate for the keep condition. Okay. So like, what is the word filter? Like, I think you're right. Yeah, so this is the keep condition, but I always reverse this. Like if you filter, when you're filtering water, right? The filter is holding the dirt and the water goes through. So anyways, just write this on your cheat sheet so you don't get it wrong. If you're filtering something, the predicate that you give is the inclusion sort of requirement. So we can filter things that are bigger than A out of here. What are the strings that are, or sort of characters that are bigger than A out of that string? Is it everything? No, it's just the lowercase letters, right? Because all of the lowercase letters are ordered further than all of the capital case characters. I'll just give you a reminder then. Okay, so let's just build filter. Should be easy as well. All right, so filter, prime. We take what? Something that's predicate. And you give me a list of A, and I'm going to give you back a list of A. Okay, so easy things. I don't care about the function because on an empty list, I should just return the empty list. All right, what about if I filter on this predicate P, and I can do this now, right? Because there's no baggage. I can actually do that pattern match. What do I do here? Well, if it's the case that Px is true, then I want to include X and then just recurse. Something like this. Otherwise, you just exclude it, right? Did I do something wrong? Something like this. Let's see if that works. Filter prime things that are greater than 0 from this list. -2, -3, 4, -5. Hooray. Okay, in edge case, let's take this out. Okay, cool. So again, not sort of the most interesting high-ordered pattern yet. It's defining filter. Okay, so here it is with the list comprehension. You can just say X such that X is drawn from X is PX, right? List comprehension sort of had the filtering built in. So this is fine. Or we can define it recursively. Or because this is a branch with exactly 2 branches, this would be an okay place to use an if expression if you wanted to. For all, this checks if every member of a list satisfies some predicate. So all is essentially for all. All of you should have taken 1061. So you're familiar with for all and there exists. Am I giving everyone nightmares? It's a beautiful course. It depresses me that so many of our computer scientists hate it. Okay, so but this is effectively going to tell you if I give you a list, if every member of that list satisfies some type of predicate. Now, I'm now going to show you this class constraint for foldable, which in your mind, you can like totally just regard as list. All lists are foldable. In fact, this is sort of a new class of foldable types. Really, so when we learn folding at the sort of end of this lecture, we're going to realize that we can fold through many things. Now, if I want to check if a structure elements are all true according to some measurement, that thing doesn't have to be a list, right? That thing can be, all that thing has to provide is a way to iterate through it, right? So it could be a tree, it could be a graph, it could be anything else which has a walkable structure. So it is at least the case that this all function is going to work on lists, but it can actually work on anything which you can walk through or iterate through, or in Haskell parlance, that is foldable. Okay, so let's just take a look at here. Is it the case that every member in this list is odd? No, because 2 is even. Is it the case that all members of this list are greater than 0? Yeah, that should be true. Okay, so let's just make all. That should be quite easy as well. So all prime, you need to give me a predicate that takes A to bool. You also need to give me A, and then I'll give you back bool. Okay, baggage. We need to figure out what to do on the empty list. That's up for some debate. All prime at this predicate, x con x's. Okay, so what do I do here? We need to short circuit, but what does that sort of mean? Okay, so what is it that if P passes through this, what do I do? Yeah, then I have to check the rest. Okay. And oh yes. And if it doesn't pass, what do I do? That's going to be false, right? Short circuit out. Okay. So I think that works. Now we just have to give some consideration to what happens at our base case. Now let's go one up. Well, okay, let's do it this way actually. How many how many datas are in bool? 2. Okay, so how many options for line 6? Well, there are 2 options for line 6. One of the options is correct, the other one is incorrect. So okay, so okay, we must be missing something here. Okay, this can't be right. We need an and somewhere. No, we don't. I guess this is what this implies. Yeah, so okay, so what should be at the bottom here then? Yeah, because if it's false, but this seems weird. I would have thought there had to be an and in here. Like this, I think this has to be PX. Am I losing my mind? How can we do a for all without an and? For all is basically just conjunction. Okay, so let's try this one. I think that will work. Okay, for all, is everything greater than 0 in this list? Yes. Is everything greater than 0 in that list? False. Okay, let's revert back to what we had. So in this one, it's easy to see why this should be true because we're anding. And if I put a false at the bottom, then I would have created the world's best nullary function that returns always false. Okay. So if I put false there, it's wrong. And there's only 2 options. Has to be true, right? Proof by contradiction, I guess. But what, okay, let's see. Would this work? This is kind of weird, right? Because you need an and somewhere. So how come we all were satisfied with me typing this? Well, let's just try. Oh, yes, sorry, that has to go. You're right. Okay. And that has to go back. Let's see. All prime P greater than 0, that list. How about this list? Okay, what about this? What about this? Okay. Yeah, so I guess that's sort of like this is a weird type of and, right? It's saying this has to be true and then do this. Pardon me? Do both work on streams? I don't see why not, right? Because we're just pattern matching the head out of here. I think once you start filtering, then that sort of if you start filtering with list comprehensions, that changes things. Yeah, so do use these, not the sort of list comprehension equivalents. I'm just showing you the list comprehension just so you can understand what it's doing, but you do want to use the higher order patterns and not the list comprehensions. Things can go bad when it comes to streams. Okay, so here's a definition for all. Yeah, the one that uses an and. Any is effectively the same thing as for all, except, so for all, basically what you're doing is this. If you have all sort of x1, x2, x3, x4, n, all is effectively just saying x1 and x2 and x3 all the way up to and xn. And any just changes all of these ands to the ors. Okay, so like really all that would be required of us here is to go any. And then we have to change the base case to what? Because if we or true, then everything becomes true. So it has to be a false, right? Because normally the base case you want to put the identity or the zero of whatever the data type is. So this should work as well. Let's see if it's if. No? Okay, why not? Yeah, I shouldn't, I don't like doing it with the guards in any case. It should be something like this. It should be bx or that. All right, that one I prefer. That one makes more sense to me. Okay, so let's try any prime. Are any of these list elements greater than 0? Sure are. Any of them less than 0? Yeah. Okay. So that was all. That was for any. They're useful. You should use them. Okay, some exercises for you to try at home because I really do want to get to the full. Define all and any with filter and logical operations. Actually, maybe we can do this one. So, do you have any ideas of how we could define all using a filter or like maybe even a list comprehension?
Filter, we're not gonna remove everything that satisfies the condition, and then you have an emphasis at the end, then you satisfy the condition.
I like it, except that you inverted the usage of filter. So you're using filter like I would use it.
Yeah.
Okay, so I think what we can just basically do exactly what you said, but change it. Okay, so filter the list. Okay, so this is for all. And we want to check if all the members of that list satisfy P. So filter the list on P. What should remain? Everything, right? So then if you just filter on P and just check if this is the same list, right? And then you'll have all. Will this work as well as the usual all? This won't work on streams. We screwed ourselves by using equal, right? It's going to take an infinite amount of time to determine if those lists are equal. So this is semi-computable. This will not work if x's is equal to x's and x's is infinite, even though we'd have to even discuss what it means for two streams to be equal, which is going to be next week, actually. Okay, so this will work. This is the same thing for any, except effective. Well, you can just utilize the fact that not for all px is equivalent to there exists x not px, and then not over that. So I've effectively just double knotted over all, right, to create a version of any that uses for all instead of for any. But you just go back to 1061 and restudy that if you want. So I can ask if, oh, is that all or any? Well, if this is all, that should be false. If this is any, it should also be false. So hooray, it's technically a correct usage example, but not the right example. This is the thing that I wanted to get to today because it is the most important of these higher order patterns because it is the pattern for recursion, right? So you would think that the master pattern for functional programming is going to be recursion and folding is going to be a pretty important catomorphism. Has anyone ever heard the term catomorphism? Kata means downward, morphism means form. Have you ever seen any type of downward forms in your math yet? Have you been given any operation that brings you down dimensions? The answer is yes. I just want you to think of it, right? That you have worked with the catomorphism before. Who said dot product? Everyone said dot. Okay, great. No, dot product is correct, right? You have two vectors and you dot product them and you get a scalar back. That's a catomorphism. That's a downward form. You've stripped form from the input. So that's going to happen here. Like folding is going to take something like a list and return a scalar. We can also return a list, but this is sort of the when we generalize folding, this is going to be the main idea that we're like pushing things downward in form. Okay, but this is very important. So folding is the process of repeatedly applying a bivariate function to a sequence of values. Folds in Haskell can be left or right. We're going to prefer right folding for reasons that we can discuss. And the left and right folds are basically just a statement about how we should be treating these things associatively. Now, students always say that they struggle with folding, and like genuinely, I don't understand why, because ultimately the idea is very simple. There's just a few bizarre nuances. So remember how we talked about lists? And I said in Haskell, lists have spines. They don't really have sort of commas or anything like this. So if you regard a Haskell list like this, a fold suppose you just give me some like arbitrary bivariate operator O plus. So you can think like multiplication or addition there. All a fold does is it takes your list and it replaces the spine with some bivariate operator. Right? So if I were to fold over this list with an add, you would get the sum of the list. Okay, now there's some nuances here. So for one, we need to know like what to do on the empty list. I've stripped all of the brackets out of this, but at a very high level, for a bivariate function that's associated in the commutative, it would look, this is what you get, right? Effectively just looking at your list and replacing the spine with a bivariate operator. Okay, so this isn't Haskell yet. We don't have fold without a left or right variant in Haskell. So this is merely illustrative. Also, if you want to port this over to Python, it's weird that they excluded fold as one of the patterns because it is the most important pattern in functional programming. So it's not in the system, period. You have to call functools, and it's not even called fold in functools. It's called reduce. Okay, so and reduce actually is this fold, but neither a left or right one. So you should know that if you want to bring this into Python, that you're looking for a function called reduce. So the description of fold on the previous slide is insufficient for two reasons. The first reason, what happens when we have a function that is non-associative, or like the associativity matters? If I were to fold the exponentiation operator over 2, 3, 4, like what I wrote would give us this. And since the associativity of exponentiation is rightward, it's going to give us that. However, like we may want to do this instead of doing that. Okay, so we need some way to instruct fold to evaluate the function left associatively or right associatively. So the L and R in fold left and fold right indicate which way that you should be bracketing this expression. Okay, and when you fold right, all of the brackets stack to the right. And when you fold left, all of the brackets fold to the left. Stack to the left. That's one way that you can sort of remember this. Okay, so right folding the power on this list will give you that. Left folding will give you that, and they're going to be different. Right? That's important for functions which are non-associative. You will be different, so it's important, right? I think this is maybe what gets a little bit tricky. So this is still not using Haskell's fold properly because what have we not addressed yet? Baggage, right? What happens if the lists coming in are empty? Okay, so what should the base case be? What should we return on empty lists for arbitrary bivariate functions?
No, we should get info.
We don't know. Okay. Yes, and also the chat's correct. So if I were to sum over a list, what should sum of empty list be? If I were to take the product of a list, what should the product of the empty list be? If I were to do all over a list, what should the base case be? I think that was false, right? Okay, so true, sorry, and true. Okay. So in each of these cases, what we're effectively doing is picking the identity operator or the zero operator. But the true point is this is unknowable. Okay, so because it's unknowable, the base case has to be provided to fold. It has to be one of the inputs. Okay, so fold takes a bivariate operator and a list and the base case, right? The thing to do on empty list. Okay, so usually, but not always, we're going to set the base case to the zero or the identity of whatever the O plus operator is. The identity is the sort of piece of data that satisfies this, like the left multiplying by y gives you y and right multiplying by y gives you y, multiplying in the sort of ring sense. This is because this is typically what we need for the recursion to work, right? If you go back to the lecture where we were just talking about how to work out base cases, this is all we did. We said, okay, go up one and then ask what you need at the bottom. And it usually was just pick the value that doesn't screw with the current value, right? The thing that won't change when I sort of apply myself through that function, right? So again, like adding 0 or multiplying by 1 or ANDing true or exponents to the power of 1. Okay, so the actual types of fold L and fold R are as follows. These are two things that definitely should be on your cheat sheet because I always forget them. But you give me something foldable, anything that I could walk through, because we could do this with the tree if we wanted to. And I think probably on your one of your tutorials, you're going to be writing a fold through a tree. We could write folds through expressions if we wanted to. We can write folds through anything that we can define an enumeration through, right? But you can just see this as list if you want. Okay, so give me something that I can fold through. Give me a function b to a to b and a base case b, and sort of this is sort of indicates structure over A. So this is going to be new, right? We're going to be able to imbue structure over types. And the structure here, I guess you can just see as list if you want. And we're going to return B. Folding from the right, this operation changes a bit from A to B to B. And you give me B, something with structure over A, and I'll give you something back B. So we're going to do a lot of examples to try to understand like the nuances between this left folding and right folding. But you should know the examples I gave you so far were very simple in that the operator I gave you was always A to A to A. I don't want to give you the impression that that always has to be A to A to A because it's not. It's usually not that in order to do something more complicated, but we're going to flesh those out in examples. Okay, so these are the two function sort of annotations that we're going to require. Try and remember it, write it down, or keep it around. It is sufficient for our understanding to use these simplified types, right? So if this really scares you, just okay, you can write this down on your cheat sheet. Folds. Okay, so here's the definition of fold R. Okay, when I fold, it's a very magical function, wouldn't you say? Yeah, it looks kind of familiar. So we'll talk about that. So indeed, this was the pattern that you were to discover on your AA1, except there's a little bit of we just added an incrementer into it. So you wrote a fold function, which also counts from zero. I hope you did deduce that. I'll show you how to work with that, and we're also going to use folding to define these base conversions in a second. Okay, so if you want to fold right, it's defined like this. So when you have an empty list, you just give me back the base case. I called it V for some odd reason. Otherwise, take something off the head of the list, send it through F. That's going to be, so F is the bivariate function. X is going to be its first input, and its second input is going to be the result of the fold. So this is like a base case, and this is a recursive. This is like the form that every linear recursive function has to take. Like definitionally, it has to be this base case and function recursive call. Right? So you know how I said in like how we write like recursive functions is effectively just figuring out how to take the answer on a smaller input and the input that you're holding and reconcile them somehow. Like F is effectively the induction, if you want to think of it that way. How do I connect this level with the recursive level? So that's a linear recursive function. So folding right is the master pattern for linear recursion. I'm going to just fold some pretend operators over some lists. This isn't Haskell code, but it is useful for illustrative purposes. Okay, so if I fold right, this bivariate function with this base case over that list, this is what effectively gets evaluated. So brackets stack to the right, and the base case is the last thing that gets utilized. If you want to, if we're going to fold in the curried fashion, it sort of looks like this, right? Or like this. Right. So usually what we're going to do, I write this down in a piece of paper and ask, like, what does the hash function have to be in this case to accomplish the thing that I want? Right. We're going to do a bunch of examples utilizing that philosophy. Okay. So this is how right folding works. Here's left folding. Okay. So left folding, it has basically the same function input, except this has been the A and B have been switched here. We do the same thing on an empty list. We return some base case, but now look what has happened. We've changed the evaluation order a bit. So we're going to fold left on this F, and I'm going to give it this. So this now becomes this is the master pattern for tail recursion, which is why right folding is preferred to left folding, because generally not tail recursion is preferred over tail recursion in Haskell because of the lazy evaluative structure. Okay, but we're going to have two master patterns now. One for linear, like primitive recursion, and another one for tail recursion. This is how it looks like. So if I fold this sort of pretend hash bivariate function over 1, 2, 3, 4, you're going to see all the brackets stacked to the left. And the base case is the first thing that gets dealt with, although it's sort of the last thing that gets put in, right? But it's a delayed evaluation. Eventually, it's going to be the first thing that's going to be handled. If we do it sort of with the curried fashion, in the fold, our slide line 4. Is it missing an F? Yes, it was. Sorry, I did correct that. I'll upload that later. They're saying there's a missing F somewhere. Is there a missing F? I think the Blackboard slides have a missing F. I don't think mine has a missing F. Okay, so this is left folding with the bivariate function. So bracket stacked to the left. Base case is the first thing that gets dealt with. If we want to look at it is in its normal sort of curried fashion, you get a function that sort of looks like this, right? So you see the last thing that happens is buried in all of the brackets. Okay, so here's a bunch of like general patterns, right? So this is sort of the generic framework for a magic style problem. I sort of say, okay, here are 3 different things that I want you to do, implement them in exactly the same way, and then let's try to apply a pattern over them. So here's the following functions for summing a list, taking a product of a list, and catting a list. That is to say, you give me a list of lists and I'm going to concatenate them together. In each of these, you're going downward a form. You're taking a list, you're getting a scalar back in the first 2. And the last one, you're taking a list of lists and you're getting a list back, right? So that is also a downward form. How can I define these with left and right folds? Well, so for sum, we can fold right the addition operator with the base case of 0. Right? That's effectively like this is literally replaced by folding, right? There is the f of x. There's the rest of the fold. Same for the rest of them. How can I get product? Well, product is just folding right with multiplication, and we stop at 1. How can I do a concatenation? Well, that's just folding right the concatenation operator, and we stop at base case. Okay, so let's do some examples to see if we can delineate between left and right folding. We can choose any base case that we want. I'm not saying it always has to be the identity. There may be good reasons to not make it the identity. So I can like fold left starting at 10, right? And the result of this is going to be 16, right? 10 plus 3 plus 2 plus 1. What's this function going to do? Yeah, it's the world's greatest zeroing function, right? It's a linear 0 function. I'm the best at programming. Okay, what about this one? Now, be careful. This is a good exam style question. I'm saying I want to concatenate all of these lists together, but the base case is not an empty list. I'm going to now put, the base case is a list with an element in it. Now, is this 0 going to show up on the left side of the list or the right side of the list? Left? Okay, let's try to reason this way through. So this was a left fold. I said all the brackets are stacking to the left. And the base case is the sort of the first thing that gets dealt with. So it's the first thing that gets dealt with. So it should be the first thing in the list. Okay, right. Okay, I guess since we already know that this is left, that's going to go right. But let's try to work our way through it, right? So we're going to fold. All the brackets are stacking to the right. And the base case is the last thing that's going to get dealt with. So that's why it's going to be on the right. Okay. I'll let you do this at home. There's the answer. Okay, so I want to start doing some practice now, and I've loaded them up into here. It's the first time I've gone through these examples in class, so do help me if I start to struggle, but I think they're very informative. So I put the patterns for left folding and right folding up here, and for each of these problems, we're just going to ask, what do we have to make this in order to accomplish the goal? So the first thing I want to do is determine the length of a list. I'm going to use 1 dash. I'm going to say length. Okay, we'll have length. Line 7? Oh, I made line 4 and 7 the same. Let me just go and grab. Thank you for that. I think I wanted to grab this. Yes. And I'll just put the letters back. A, B, C, D. Thank you for that. Okay, so let's do length. I'm going to put a prime. We'll use 1 prime for left folding and 2 for right. Okay, we'll do each of these twice. So what's the type signature for length? What kind of list? What kind of list can I take length of? Any constraints? No constraints. Okay, so I take A, I return an integer. Okay, and I'm going to say that's undefined. And this one is the same. I'm going to take A and I'm going to put an integer. And I'm going to call that undefined. Okay, let's load this in. 6A. Great. Okay, so I'm going to bring the left fold pattern down. And let's just think about it. What do I have to do? What does this have to do in order for me to get out of this? What do I want out of this? 4? So how can I define that hash? Like, what do I define this function as, right, in order for that to be 4? +1? How can it be +1? That's a unary function. Remember, this hash function has to be a bivariate function. Okay, so I'm going to start writing stuff. So we're going to fold left. And I always forget what the signature is. Fold left. Okay, so fold left. And we give it a function. Okay, so a function has to go in here, foo. Then I give it a base case, b, and then a list. So I'll be fine, right? So I have to define foo in b here, right? Because the point, remember the point free form? I don't actually have to include this on both sides. That I'll get rid of. Okay. Yes.
This that takes in any input and just returns +1.
That's still a unary function. Okay, let's start with the base. That should be easy. What should the length of an empty list be? Okay, so that's sorted. So what should this foo be? Remember, it's a bivariate function. So I'm gonna start us up. So there's here's 2 inputs. What should they go to? Yes, sir.
Well, the fix an element of which returns the
It takes an integer and an element of a list and returns integer. Yes. Integer +1. Well, here's x and y. Can you describe what you said using x and y? X +1. Anyone agree? For what?
Check that it's not empty.
The fold will do that for us. Yeah. Okay, let's see if it will work. Length prime 1, 2, 3. It works. Good job. Right, because what do we need this to do? We need it to return 1. It's okay, so that will be 0. So we always need it to return the first input plus 1. Right, for whatever this, I don't care what the second thing is. I'm just dropping it. Right, so just give me the first thing plus 1. Okay, so actually, that's fun that I can do this. That's actually the successor function. And then we also don't need this. Okay, let's do it the other way now. Here's the right fold pattern. What do I have to do to get that to equal 4? Okay, well, it's going to be a fold right. So I'll put a fold right in here. Some function has to go in there. What's the base case? Okay, so it's still the case that empty lists have length 0. Well, what should I do here? So what should this do? So I'm going to take x and y, and what should I do with it? Y +1. I need to say, oh, this, what's the length of this list? Well, it's 1 plus the length of that list. That one's the easier. I think that's the easier one to understand because the right folding is the linear recursion, right? So it's just, this is going to be the length of the list of like -1. So what is the length of this list? Well, it's 1 more than that. So I can just say I don't need x and I want to go to the number after y. And let's see if that works. Double prime, 1, 2, 3. Length of 3. Length 1. Length 0. Cool. Okay, so but notice here, like we no longer are folding with a function that's a to a to a. Right? These were different. I think this was like a to int to int, and the other one was int to a to int. Okay, so that's when these foldings get like sort of more useful right? When you're defining functions that aren't A to A to A. Okay, so we'll get rid of that one. So good job with the length of the list. Reverse a list. Okay, so let's do rev prime. So what kind of list can I reverse? Anything gives me anything back. Okay, so I also want this, but a right folding version. So rev prime has to be a left fold. Rev double prime has to be a right fold. Let's work on the left folding one first. Okay, so what has to happen with this list? This has to eventually be equal to DCBA. All right, so is there any freebies here? So a function has to go into here. The base case has to go there. What's the base case for this one? Empty list, right? Because the reverse of an empty list is a what? Empty list. Okay, what should go here? Okay, so I'll say X and Y. What should that go to? Well, let's look through here. So this A eventually has to go to the back, right? This V we've said is what? An empty list? So it seems that what this has to do, at least in the very first position here, is put A in the front and well, connect A with V. Yeah? So this has to be something like connect A with V. Oh, sorry, that's the wrong spot. Connect A with V. Okay, let's give that a try. Oops. Reverse this list. Hooray. Okay. A funny thing about functions like this. So this was a function that just flipped the input to something. Would you agree? Like it's taking X, Y, and then it's saying, oh, go Y, X. Funny enough, there is actually a higher order pattern for this. It just permutes the input. So actually, we can reverse like this. Cool beans. Okay, what about the right fold? So what do I have to define this as in order to get that out of it? Now, again, I believe the right folding one is a little bit easier because that's just recursion, right? So if that's recursion and it's working properly, out of this is going to come what? Well, the reversal of, okay, so remember, we're reversing A, B, C, D. We're going to say it's going to go through this pattern, right? So therefore, what's going to happen when this resolves itself? This is going to have the reversal of the tail of the list. Yeah, we just have to put A on the other side of that. Do you see? Right, so all I have to do here is say that this is a fold right. Empty list get reversed to the empty list, but I want to take X and Y and say that X just gets concatenated to the back of Y. Will that work? Yes, it does. Okay, I don't like this, but I don't like reversing lists, period, right? So it doesn't surprise me that something imperative required an imperative type of solution. Yes, sir. I would believe so, yeah. It's like there's actually something called fold left prime. I don't know if I want to talk about this. Do you know how I said in tail recursion there's a problem because it leaves all of the computations happening in the accumulator till last? This forces it to evaluate, right? So does that make any sense? I don't want to flesh that out any more than I have to. Fold L prime does away with the disadvantages of tail recursion in Haskell. Let's just say that, right? By forcing the thing that's usually lazy to be eagerly evaluated. So, but I don't care. We don't care about efficiency in this class, but I suppose I should mention it. If you type in which is the preferred fold in Haskell, there's like a big argument about this. First, they'll say right fold philosophically, that's the one that we want to use. But technically, fold left prime, this optimized fold left could do better. Okay, but at least in my mind, I have an easier time grappling with the linear recursion than I do with the tail recursion, but it seems to be, 50-50. Okay, so that was reversing a list. Base 2 to base 10. It's a question dear to our hearts. So let's get two usage examples here. So I'm going to say, we'll do this. Okay, so you're going to give me a number, something like 001, and this is a base 2 number. And so I'm going to say that this is equal to 6, right? So that its least significant digit is the thing that's first. Okay, let's just write this. How did I say this? 2 to 10, something like that. So this is a function that's going to take, I'm going to say a list of integers, and this is going to return an integer. It's going to be something like it takes this, and then we get back 6. Okay? So I'm going to do this in the linear recursive fashion, and then we'll immediately write our right fold. So what binary number corresponds to the empty list? 0. I think that's fair. If I'm going to take a binary number and pop out its least significant digit, and those are the rest, what's the recursion here? Okay, so we're always doing the same thing. I'm always going to say, well, just go ahead and tell me what the base 10 number is of the rest of the number. Okay, maybe I need to write something out like this. This is going to be a base 2 number, right? Something like 0 times 2 to the 0 plus 1 times 2 to the... Okay, I'll do it with bases. So every base number is going to be something like b naught, b to the 0, plus b1, b to the 1, plus b2, b2 times b squared. So b is the base. You can just think about it as 2, but it can really be anything. bn, b to the n. Okay, so if, I'm going to call this x. So what is, if I take x and I mod x out by b, what do you get? B naught, right? Because if everything here has a multiple of b in it, right? So if I mod out by that, it's like multiplying that stuff by 0. What do you get if I take b and I divide it, or if I take x and I divide it by b? Well, you get this number back with all of the exponents shifted down by 1. Which means I can, if I take this and multiply it by b, then you put it back up by 1. So I'm just going to do this. That's the least significant digit. Then I'm going to say, go get the base 10 conversion of the rest, but divide that by b. Oh, sorry. No. I've screwed this up. No, that was correct. Yeah. Right. So this is the tail of that. Right. So when I ask the recursion to go get me the base 10 expansion of that, it's going to be divided by 2. Right? Because I shifted everything over by 1. I removed its least significant digit. Okay, so this should work. Yes. All of you have opinions now after seeing the answer. Okay. Well, that's still no? Okay, so let's try 2 to 10. 0, 1, 1. That should be 6. This should be 7. That should be 5. Okay, so what is this the pattern for? Left folding or right folding? Well, is this okay? I'll write it like this. It's right folding. Okay, so let's try to now make this a right fold. Okay. So how can I do it? This is a right fold. 2 to 10 prime. That's the one we're going to designate as right folding. Okay, 2 to 10 is equal to a right. Oh, so double prime for right folding. That's equal to a right fold, some function. What's the base case here? Yeah, here, right? It's just 0. And what do I have to put into here? Yes, x plus 2 times y. So 2 to 10 double prime, 1, 0, 1 should be 5. 13. Okay. So that was the right folding. Now, can we do this with left folding? Is the new question. I'll get rid of some of this. This is a little bit more tricky. Okay, so the answer is like to do the same thing that we just did with left folding is going to be like it won't work. However, I can do this question. And okay, so I'm going to define something, then we'll talk about it. 2 to 10. And I'm going to left fold some function. The base case is still going to be 0. And what am I going to fold? Let me see if I can remember this. I think it was 2 times x plus y. And I'll show you what this does. Okay. 2 to 10 double prime. 1, 0, 0. Wait. 5. Oh, double prime. Sorry, I need to use single prime. So this is the thing you're telling me was impossible to do without reversing? Didn't I just do it without reverse? So this is the problem you had, right? Where the digits were listed from most significant to least significant. And that's the answer. Okay, so I'll show you how this is working. Let's take the right fold pattern and study what's happening. Where's the right fold pattern? Oh, sorry, not the right fold, the left fold. Sure, here's the left fold pattern. So what am I saying the left fold pattern is doing? I'm saying this is an infix operator, which doubles this and then adds like what remains. Okay, so what is that equal to? That's going to be 2 times v plus a, which is 2 times that, plus b, which is 2 times that, plus c, which is 2 times that, plus d. Do you see all of these 2's stacking? That's giving you the power of 2 that you require to multiply the most significant digit by ways of tail recursion. So you didn't need list reversal, despite all of you yelling at me over the EdStem that this was impossible. It wasn't impossible. In fact, it could have been implemented with one fold. Also, you could have just done it the easy way and just put a reverse there. That would have got you perfect marks. But this is the sort of more satisfying answer. Okay, let's do one more. So everyone like that one? I sort of like this one. So, and of course, you could just replace this with instead of putting a 2 here, you put a b. And then sort of you're off to the races. Okay, so I'll get rid of that. I'll be sure to post this. Here's the magic question from 2002. But I'm going to sort of make it a little bit more nuanced than this. Okay, so the question is this. We want to define a method called last, which takes a list of A and gives you back A. But we've defined this to be the case. And undefined special, you can't define. As soon as you evaluate undefined, you throw an error. So this doesn't count as a pattern. This basically counts as raising an error. Okay, so you want this is we said we want a function that gives us the last element of a list. We are going to define. We're going to say that it's undefined to ask for last of an empty list. Which fold can we utilize here? And it's only one of them. And then we utilize it to actually solve this problem. You reckon it's right folding? Okay, so we're saying it's this one. So what do I define this function as in order to eventually have it return D? You can't. Okay, so it's not right. Right folding is not going to work here. What can you define hash here so that it eventually returns D? Abstract this away. What does that function have to do to return D? Return its second input. Okay, So this is all this has to do. This is equal to a left fold when you give me this function, which simply gives me back the right input. And what should we put as a base case here? We have to put something. What should we put? Didn't I delineate the base case here at line 13? This is undefined. Okay, let's see if it works. Ta-da! Higher order patterns are the best. Okay, so you have to know how to use fold. Fold is the most important higher order pattern. It's recursion. Okay. Singleton list, I think that will work as well. Right, because you can evaluate. So here's a lambda function x, y that goes to y. And I'm going to say, yeah, can I give it one undefined? All the way around? Okay, anyways, we can do it in such a way that it doesn't, remember, it's lazy. So it doesn't actually evaluate x because it doesn't have to. And that's good because that was undefined. Okay, so those are all the folding examples. There are some practice for you to do at the end of this if you want, but I think the main fun thing today was doing the base conversion. Okay, is there any questions regarding folding before we move on to product types? Okay, so do get some practice with folding. We're going to need them, right? They're going to be really, really important because they're going to allow us to, let's see if I can actually do something. Like we're eventually going to have lists like this. And I'm going to want to say sum the elements of that list together. And we want to do so in one line. We don't want to do so by stripping just off and putting them back and asking if something is nothing. So I'm going to want to fold through this with more sophisticated type of expressions, specifically something like this. Eventually, I'm going to say I can map this add to the applicative of just one with just two. And we're going to talk, we're going to talk a lot about like ignoring structure or jumping into structure and doing something. This is not like, so this is impressive already because in one line, we're managing a lot of functionality where we'd normally have to like decorate and undecorate these things. But the true advantage using this is that this has all of the nothing functionality baked into it already. Okay, so this is going to allow us to do error handling. So soon, but do try to gain a mastery over folding. Okay, algebraic data types. And I need to refresh my coffee. I can't believe you guys don't drink coffee. For one, you're university students. And two, this is Australia, some of the finest coffee in the world. Right? The coffee we have in Canada is just sort of like brown water. It's nice. You can drink like liters of it. It keeps you warm all day. So when I first got here and started drinking liters of Australian coffee, I think I induced an anxiety attack. I'm like, why am I shaking? You ever see that one Futurama where Fry effectively like, yeah, ascends to the next level? Shut up and take my money. That's where that meme came from. Do you know that meme? The shut up and take my money? Yeah. And Genesis and Futurama. Okay. Algebraic data types. Okay, I don't know why there's a W down there, but hello, W. I think the command to exit a window is command W, so that's why that's there. Oh, we have some questions from the chat who we shouldn't ignore. The decks in the lecture theater aren't big enough to manage coffee cup. Oh, well then no laptop, use the coffee. You know, I went to university, none of us had laptops. This was like a luxury. We didn't even have wireless internet when I went to university. It sucked. We had to like go everywhere by riding dinosaurs. It was like, it's bad. You guys won't know what it means to trudge. You know what it means to trudge? Oh, have you lived abroad or do you just know it? You're just well read, I guess. If you're like walking through like 1 meter of snow, you don't walk through that. You trudge through that. It's trying to get to school, right? So I had to walk to school in like 40 below, uphill both directions. You know how it always works. Bears chasing me down the street, which are like, bears are sort of like sharks, but on land, right? They're pretty fast. Like you imagine a bear is slow, they outrun deer. right? They outrun deer. Like people go to Canada all the time and get killed by bears because they're like, oh, they're cute and cuddly. It's like it's an omnivore. It's going to kill you, and it's not even going to kill you efficiently. If you want to get killed by an animal, pick like a cougar and then like expose your neck or something like that. If you don't want to, so there's a joke in Canada. It's like two guys are walking through the woods. And the guy goes, oh, there's some bears around here, so we have to be careful. And his friend says, don't worry, I'm pretty fast at running. And the guy says, you're never going to outrun a bear, mate. And he says, I don't have to outrun the bear. I just have to outrun you. Right? That's the joke. You can also climb a tree. That's if you want a really good view of the bear before it kills you, right? Because bears are also very effective at climbing trees, right? I don't know the genesis of the bear memes, but I do love it. So I'm trying to get the UQ Computing Society to like change the shark to a bear. Okay. It's going to kill you. It's going to kill you, and it's not even going to kill you efficiently. Yeah, I think there's somewhere on the internet a collection of insane quotes that I've made. You can find my extremely dank story about how I once stole candy from sick children on Halloween. You'll have to find that one, but it's online somewhere, and I'm not even exaggerating about what had happened. If I'm in a good mood one day and we have some time, asking about how I stole candy from literal sick children. Okay. So custom data types are among Haskell. Speaking of sick children, custom data types are among Haskell's most powerful features. Use them. So we want to use data. Like taking data and transforming that data is the name of the game in Haskell. So writing code with pattern matching, type checking, and inference makes your code safer, more concise, and thereby easier for other people to read. Right? And this is a key for working in industry. Right? Programming in Haskell is hard. Have you realized that after doing A1? I think A1 typically is like one of the most difficult assignments in this course. Right? Because you have to recalibrate your self-assessed ability at programming in a different paradigm. But it'll get easier. Okay, so here's some terminology. So here's a data type called Boolean. It has a type constructor, although this is a null array constructor because it just gives you back true or false. And false and true are called its data constructors. So false and true are called null array constructors or constants because they take no arguments. The pipe symbol in this case could be read as add because this is a sum type. You have bool, it's false and true. A data type with a type constructor is like the tuple constructor, right? So here's something that actually says, oh, I'm a type, but you actually need to give me types in order for me to become a type. We're going to learn about, this is called a kind. We're going to learn about abstract types in a couple of weeks. But so here's some data which didn't have a constructor, and here's data which does have a constructor. So this is called the product type, right? Because here you have false and true. That's 1 and 1. This is called the product type because how many tuples do you have here? Well, there's as many tuples as the number of elements in A times the number of elements in B. So that's a product, right? So as soon as you parameterize a type by another type, you get many things. Right? And this is sort of why we call it a product. Okay, so here's a data type for colors. Red, green, and blue. We could also have another data type for colors, which is parameterized by 3 integers, right? So this one gives us exactly 3. This one is going to give us as many as we want, right? So I could also have colors that were RGB types and say, okay, give me an integer between 0 and 255, an integer between 0 and 255, and an integer between 0 and 255. The number of colors in here is the product of the amount of integers in int times cubed, effectively, right? So some types, product types, right? Because nothing is parameterized here and something is parameterized here, like the data constructor. Ultimately, we're going to write code to run it. Okay, so I'm going to talk about stages of execution once and then put it away, right? Because I need to tell you a little bit of something about the compiler in order to make sense of the new type constructor. So this is very wishy-washy. So don't ask me too many technical questions about this because I don't even really understand how the compiler is working. There's a lot of smart people who are programming into it. We just know that our Haskell code turns into C code eventually. Okay, so when we read a program into the REPL or compile it, this is when the type checking occurs in Haskell. And do you think it needs to type check more than once? Once it type checks, we're type checked. We never need to check types again. So this is somehow like when Haskell does its type checking, it confirms that all functions can only pass things to other functions which are allowed, and then it forgets about them. right? Because it's impossible to now introduce a typing error into the runtime of the program. Okay, so in runtime, our program is interpreted into execution. At this point, data can be created and expressions can be evaluated. There is a distinction between in runtime and compile time type constructors and data constructors. Now, the fact that we have type constructors is a little bit controversial because everything that you can do with a type constructor, you can do with a data constructor. So in this class, we're not going to use type constructors. I'm only going to use data constructors just to keep things sort of more simple. But I do have to tell you about this in case some of you go out into the wild and start programming with Haskell. Okay, so here's an example. Here's a type synonym that represents a position on the grid. Right? So remember, we can always define type synonyms in order to make our code more expressive. So instead of having integer tuples, I can say, oh, we have a position, and this position are going to be tuples of int. So I can say, okay, foo is going to take a list of positions and return a position. Type declarations can be parameterized by other types, right? So actually, we could have done something better than this position and say, oh, I actually want an arbitrary type of pair. So it's a pair of A's, right? So I could have defined a type that's parameterized. So this is now a product type saying, okay, give me a pair of A's, and that's going to be an AA. So now I can go from pairs of ints to pairs of chars, right? So this is sort of like the maybe type that we had. Type synonyms are useful, but they can lead to errors. So here's an example. I say I want to type, I want to work with names. All names are going to be strings. So here's a type function foo, which takes a name to an integer. And maybe I just want to know the length of my name. So this is going to work. I could say foo of Paul Verbeek. That's going to give you back 10. I think that's inclusive of the spacing character. But foo of a random string is just going to give you back 15. So like, what was the point of doing this? This didn't help us not construct a name that wasn't a name. So what we can do now is have this thing called a new type. And a new type distinguishes itself from types by using sort of a decorator. So a new type must have at least one constructor. Otherwise, it's going to be indistinguishable from type synonyms. So now I can say, okay, I have a new type. It's not a type synonym. This is properly like a new type that I want in the system. This new type is going to be called name. And we're going to have this name constructor over string. Now, this name is usually the same as this. They don't have to be, but it's usually the same. And the benefit now is we can define this constructor name, and then we can have that reject things that aren't that detect not well-formed names or something like that. We're going to do that later in a sort of error checking class. But that's the advantage here. Now we have this decorator, this constructor that we can actually like have, it can actually reject stuff. So now I can say I take names to ints, and I'm saying, okay, this name of x is equal to length of x. So now it is at least it's the case that when you're passing names to functions foo, you have to have this name decorator there. So this is going to prevent you from just passing arbitrary strings to that function foo, right? Because you would have to decorate it with a name. And then the hope is either this name is doing the rejection for you, or its mere presence is a signal to you as a programmer that this thing should be codifying a name and not a random string. Okay, so using new type constructors do not incur any evaluation costs, right? This is why they're really popular to use in the Haskell community, because they give your programs some clarity and there's absolutely no speed cost incurred by that. So using a new type improves safety without affecting performance, but that's all I care. That's it. I'll never talk about new types again. You know that they exist. People use them in industry because they afford clarity without getting any efficiency hits. Whereas defining new data, that actually does incur penalties because Haskell has to actually build something instead of just having sort of like a type decorator. Because the notion here is as soon as Haskell does its type checking, it can just throw away all these decorators. It doesn't care about them anymore. That was like a human thing. Okay, so who cares about new types? What I want to focus on in the rest of class now is just defining data and then defining instances for that data because we haven't done that yet. So what are some instances that we've worked with? Like what are the two classes that this belongs to? Defined it right there, right? So this is an ordered class and an equality class. So the question becomes, so when we derive them, what is it that we're deriving is the first question. And the second question is, if we don't want them to be derived, can we in fact write them? So I want to let's work with this type now. And we'll move here. Great. Okay, so here's some data. It's for shapes. It's going to be rectangles with width and height, circles with a radius. triangles with a base and a height. And we're going to derive equal and show. Okay, so let's just start playing with this. I'm going to load this in, lecture 6B. Okay, can I have a rectangle? Will that, if I do this, is this going to be permissible? Okay, well, what will it show me if I ask it to show me something? Error, right? Because we haven't derived that. So let's derive show. So now we have a rectangle. Now we have that. Okay, so what other things have we derived? Equal in order. Well, is R equal to itself? Okay, is if I have S, this rectangle, 1 and 2, is R equal to S? Good, because what is it doing? What is the derived equality operation here? It's just asking if the patterns are identical. And are these patterns identical? Yes. Okay. What about ordering? Okay, if I define a circle T, that's a circle with radius 1. So we have R, S, T. Is R greater than S? Those are the two rectangles. Is R less than S? Oh, it's kind of strange. Okay, what about, is this rectangle bigger than this circle? So there's R, there's the circle. Is this rectangle bigger than this circle? We derived it though. We derived it. So Haskell is able to work out some standard ordering for this. How? What is the standard ordering? Yeah, look at this. I typed this in, didn't I? And doesn't this induce an order on those things? So it's bare minimum the case that rectangle is bigger than circle is bigger than triangle. Okay, so is rectangle bigger than T, which is circle? Sorry for error. R, T. Okay, so maybe it's ascending. So is R less than T? True. Okay, okay. Here's a rectangle. 1, 1. Here's a circle. 1. Here is a triangle. What does chat need? Illuminate is the greatest. Okay, and here is a triangle, not traversal, triangle. Base 1, height 2. Okay. So is rectangle bigger than triangle? No. Is rectangle smaller than triangle? Yes. Is circle smaller than triangle? Yes. Okay, so it seems that this is less than this is less than this. Okay, what about this? Is circle of 1 less than circle of 2? It's smart enough, right? Because effectively, what does this look like? What is this isomorphic to? A tuple. This is totally isomorphic to a tuple. This is isomorphic to a one tuple. This is isomorphic to a tuple. And can we compare tuples in Haskell? Yeah, I think that's very sensible that we can compare these tuples, right? So when you're comparing in the same rectangle, it's going to do that tuple comparison for you because we've derived order. Okay, but suppose I don't want to do it like this. What happens if we have a rectangle that's like this, and we have a rectangle that's like this? Should we say that those rectangles are equal or greater than or less than? Like, what's a better way of actually like inducing some type of clarity or sense on order here? You want to do area. I think area is a really good idea. Okay, so here's how now we can write a custom class. Okay, so I'm now going to take order out. Okay, so you will see I can no longer compare rectangles with rectangles. So we no longer have this. Okay, so I can say, I'm going to define an instance of order for shapes. Where, what? Okay, what should I write? How do I write an instance order for shapes? Okay, so remember this? Perhaps you didn't. We can ask for information on any of our classes. In particular, we can ask for information on order. What does order say? In order to be part of the ordered class, you have to define the following functions. However, it also says minimally define compare or less than or equal, and we will be able to derive everything else automatically. So what we're going to do is define a compare operator. And let's take a little look at what compare does. No. Okay, so it's something that given an ordered type takes A and returns back an ordering. Okay, so compare takes a shape and another shape and returns an ordering. Okay, what is an ordering? An ordering is a data type that gives you less than, equal than, greater than, right? So I can compare 2 and 3. I can compare 7 and 3. I can compare 7 and 7. Okay. What do I type? Oh, so I want to compare maybe shape X with shape Y. So, and you said we should do this with areas, which I think is a great idea. So I want it, this is true when, well, just kick down the comparison to here. Savvy so far? Will it work? Okay, how do I do area now? Okay, so now I need to find an area function. So area shapes goes to what? Okay, float, I guess, even though I don't love it. Okay. So on assignment 2, you're going to have a question exactly like this, which is impossible to accomplish if you don't use pattern matching. Just impossible. How do I define an area function for that data? How many patterns are in data for shapes? Therefore, I need to figure out what to do in each of those patterns. I'll just type it in. It's exactly 3. Okay. Why should I use cases? This is better.
Yeah, is it possible?
Of course, it's possible to use cases. Yeah. So if I define these 3 things, is area going to work for every shape? So will this will satisfy the definition of area, right? So what's the area of a rectangle? There you go, guys. No, just 3. I think I'll round up actually. Yeah. Jesus Christ. When I went to university, the first week was a lot of shouting at one another. Math was technically part of science, but I was ashamed of that. Engineering would always give science so much shit. I thought it was so hilarious, right? Just watching us. They would just hold signs and say, like, science sucks. Like that. And I'm like, that's hilarious. But we had a cheer, and this is why I remember this. It's don't laugh at me. This was so nerdy. I was dying. We didn't have the word cringe back then, but that's what it was. There go sine, cosine, sine, 3.14159. And I was over there in the corner dying. I'm like, I wish I was an engineer. Guys, stop talking. Okay, triangle. 1/2 base times heights. Okay. So this is how we define area for that data in the functional paradigm. And when you're given data, and I'm saying, write me a function that's total over that data, all that is required of you is to ensure that you've just defined a pattern, a function for each pattern in the data. That's the philosophy here. We don't have to think about all these strange edge cases because they're just delineated for you. Look at your data, make sure that you've defined a function for each of the patterns in that data. Okay, so let's see if this works. Can I now have, okay, I'm going to have a rectangle. Whoops. Okay, I'm going to have a rectangle 10, 10. I'm also going to have a rectangle 5, 20. Here's X, here's Y. What happens if I compare X and Y? It will work. Okay, hold on. I'm going to do something else. I'm going to take equality out. Whoops. Why is it complaining now? Huh? What? Why is it complaining when I take out equal? That shouldn't matter though. Like that's the thing. Sorry guys. If I take that out, where in here have I ever done a shape equality? No, that's the sort of point I'm trying to make. This equality isn't the same thing as this equality. That's the point I'm trying to make. But I don't know why. Okay, I'll have to follow up with this on EdStem. But that's bizarre. I'm not doing any equality on shape unless that pattern matching is somehow inducing it. Okay, but this is the point I want to make. This equality isn't the same thing as this equality. This is the ordering. How can I put this? Not all orderings are strict total orderings. Does that make any sense? Okay. I can order lists based on their length, right? So a list of length 3 is bigger than a list of length 2. But how many lists of length 3 are there? Lots of lists of length 3. So all the lists of length 3 in the ordering by their list length are equal. That's what that equal is. Equal in the ordering. Not equal generally speaking. Equally ordered. So it's a different equal for comparison than this equality, which is actually sort of mathematical equality, not equality in the order. I don't know why. I'll have to go back when I'm not in front of like 100 people or 1,000 people. YouTube can't see the audience, so I just have to tell them that it's just super packed in here. Okay. The herd thins. There should be 300 of you. It should be full. Okay, so that was how we can do area. So let's just check that this is working. So I have a rectangle that's 10 and 10. I have a rectangle that's 20 and 20. And it should be the case that, okay, if we compare R and S, we get that. But Haskell was already able to extract all of the functionality for everything else just based upon the fact that we've defined compare, right? It did so automatically. So that's pretty cool. Okay. So there we have that. There is our area function. Okay, so I want to just do a little bit of recursive data types. We've done lists, so let's just not do lists. I think what I want to do is talk about, so here's a custom class instance for show. We never did it. I'm less interested in that. This one's interesting. Have any of you taken set theory? Do you know how the natural numbers are defined in math? Why? Who told you? Who told you? 2048? Okay, so what I'm going to do right now, because there's going to be a question on your, I want you to prove that addition is commutative, I think. Yeah, prove it. It's something that you all know to be true. I'm going to have you prove it on A2 with induction, of course. Okay, so I just want to show you how the natural numbers are defined. So we can have some data for natural numbers. Let's just build them. What do you suppose the natural numbers should be? Can you give me at least one natural number? Oh, boo, get out of my classroom. They said 1. Oh, sorry. Can you give me the least natural number? Okay, so let's say 0 is part of our collection. What else should be a natural number? And this is the interesting, we can use recursion now. Like these can be self-referential. Any natural number plus 1. Yeah, so I can think, let's just call that successor. So the successor is the thing that comes after a number, or let's just say next then. But in your homework, it's successor. So I'm going to say with successor, but I'll just put here. You know, if you want to think of this as next, you're quite welcome to. Okay, so the natural numbers are defined, or we can define them right now, as 0 or something that comes after a natural number. Okay, and let's just do derive show. Okay, so I can say something like 0 is 0. 1 is the thing that comes after 0. 2 is the thing that comes after 1. 3 is the thing that comes after 2. Let's do one more. And 4 is the thing that comes after 3. Okay, if we look at this, here's 0, here's 1, here's 2, here's 3, here's 4. 4, like it's the thing that comes after 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 0. This is literally how the natural numbers are encoded in math. We don't use the successor operator, we use a union operator, but it's effectively the same philosophy at play here. My question is now, can we define addition for this? Okay, so what's addition? And we'll use our philosophy. Okay, I'm going to say I need to take two natural numbers and return a natural number. And I said all we have to do is make sure that we've covered all of the patterns in the data that we have just defined. So what are the edges, I guess? Well, I got to be concerned about 0. Maybe I also have to be concerned about this 0. Actually, those may be the patterns. So what is the sum of, what do I get if I add x and 0? What if I do if I add 0 and y? Y, okay. Here's the, okay, let's just do this. I'm going to say this is x, and then I'm going to match a pattern here. Successor of y. Okay, because by this point, I know I can do this because it is not the case that the position here is 0. Because I've checked for that here. So if it's not this, it has to be this, which means there is this successor that I can pull out. So therefore, this could be equal to what? Well, I always want to do a recursion. So what is, this is sort of like x and y plus 1, if you want. And I'm saying this is equal to something when I add x and y. And what's that something here? Plus 1, isn't it? Which really is what? Successor. Okay, so actually this is just successor. So here's 3, here's 4, and here's what we get if we add 3 and 4. Okay, that's addition. Because we were never really we're never decreasing the first position. I think this pattern is actually not useful. It is useful because if you give x 0, then it will happen faster, but we don't really care about fastness. There you go. Okay, so that's one definition of addition. Which is this tail recursive? No. So what kind of recursion is it? Yeah, primitive linear recursion. Okay, this is not the one that we're going to give you on your homework. On your homework, it's easier to work with tail recursion. So we're going to give you the tail recursion one. Can we change this to be tail recursive? So that just means basically I'm only allowed to call the function again with different input. What different input should I choose? So this is kind of like you're stripping plus 1s off y and giving it to x. And eventually y is going to run out, become 0, and hit this. So this will also work. Whoops. Add prime. Okay, so now I've defined addition in Haskell. And I can say here, we've defined this in Haskell, prove that the way that we've defined addition gives us commutativity. And that's what we're going to have you do on A2. It's either commutativity or associativity. I sort of like permute them every year, but it'll be one of the two. I think associativity is harder. So you hope for commutativity. Okay, so that's what you'll be doing on your homework. That's pretty cool. Okay, let's just do this. Let's write a function to convert int to nat and vice versa. Okay, so int to nat. So give me an integer, and I'm going to give you back a natural number. How can I do this? So what's the base case here? 0, right? I can't convert -1 into nat. So this is equal to what? 0. Okay, int to nat of x. Yeah, the successor. What comes after int to nat of x minus 1? That should work. Int to nat 100. A lot of Oh, it's Lisp. Look at that. Okay. Anyone? If you knew, you would find that joke hilarious if you programmed in Lisp. Okay, what about nat to int? Nat to int. We want to go from a nat to an integer. Okay, what's the smallest nat? 0. What integer should that be? 0. Okay, because we've checked for 0, I actually am guaranteed that I can do that pattern match, yeah? So if I can do that pattern match, what do I want to do here? 1 plus nat to int of x. Oops, I got to give it a number. What? Nat to int. Oh, I got to give it a nat. 4? 4. Funny enough, successor is already defined in the system. We've discussed that before. So really, actually, this was this, just to make things a little bit more confusing. That will also work. Okay, cool. One more exercise. Oh, we've done adding two nats. Oh, try doing subtracting two adds. We could do multiplication too. Can we do multiplication? Okay, if we have time, maybe we'll do mult. Write a data type for binary trees and give a function to convert the tree into a list. Has everyone here worked with binary trees? Okay, so this is a tree. I don't, oh, great. Reorder. Here. No. Preorder traversal. Who is yeah, here. Okay. Where's the picture? Here. I don't know. Okay. So this is a tree. It's just like a list, but like the list, every element can go to one of two elements. So like here's a tree. It has this is called the node. And then every node is connected to a left tree and a right tree, which can have nodes and left trees and right trees. Okay. So I could very easily make data for that. Okay. So we can have a data for a tree. Okay. It's data for a tree comprised of integers. And we can have a node with an integer in it. Oh, not integers. Or I can have a tree that has a tree integer in it. Left tree, right tree, and then maybe some integer. I hope I did that right. I feel like I've screwed something up. I don't think I actually have to parameterize it if it's just an integer. I have to hit my emergency backup button. Where is it? Oh, it doesn't like being parameterized by, I think, concrete types. Okay. Okay. So here's a binary tree. We're going to put A in the nodes. And the nodes can have leaves, right? So a leaf is going to be the thing at the bottom. It's special because it doesn't have anything coming out of it. Otherwise, let's move this here. Otherwise, it's going to have a left tree or a right tree or the thing in the middle. Okay. I have to hurry. Okay. So I can have a tree. And I can say, let's connect this with a left tree. So this is maybe leaf 1 with 2, leaf 2. So we got a tree that sort of looks like this. I actually yesterday went ahead and where is the tree? Here. Okay. So that is the tree displayed here, right? It's a node F connected with this left tree and this right tree. So you can see it's the node F connected with this left tree and that right tree. And we can do something like a pre-order traversal through it. I'm rushing through this one, but it's okay. It's not too important. You're going to go over this in your tutorial this week. So I want to do a pre-order traversal of this. If you know, you know. So it's basically just going to turn a tree into a list. And the way that it does it, I'll give you a little lesson here. Oops. Why did it do that? Okay. So these red dots, so what you write a tree and then you walk around the tree. And you list the tree the first time you pass it on the red. That's an in-order traversal. If you list it after you pass the green, that's called an in-order traversal. And if you list it as you pass the blue, that's a post-order traversal. This is stupidly easy to write in Haskell to do the pre-order traversal. So I said, all we need to do to write these functions is make sure that we have one thing for each piece of data. So how do I do a pre-order traversal on a single leaf? Well, how do I do a pre-order traversal on something that is a node with a left tree, a value, and a right tree? And that is just X connected to the pre-order traversal of the left tree plus the pre-order traversal of the right tree. So again, you'll do this more in tutorial because I want to do the derivatives next. I am screwing things up. What did I do wrong? Why is that oh, list A, sorry, list A, yes. Okay, so I can do a pre-order traversal of that tree, and you get that. Moving this X around, so this is in order traversal. I'll just show you this. This is in order, it's in the middle. Yeah. This is in the middle. That's in order. That's post order. So the in, post, and pre just designate where you're actually putting this X in this expression. Okay. The last thing I want to do it in 10 minutes, and who thinks I can do this? I want to define a function for taking derivatives of polynomials, arbitrary polynomials. 10 minutes. You think I can write a basic computer algebra system in the next 10 minutes? Okay, what do we first need? I need data for polynomials. What's a polynomial? Great start, guys. No, a polynomial is something like this, right? You can have like 3x squared plus 2x plus 1. That's a polynomial. Okay, so I need some type of data type for that. So like what is this broken up into? What is the smallest thing in this polynomial? Yeah, I think it's something like this. What do we call this? A term. Specifically the leading term, but generally a term. So I'm going to say polynomials are terms of integer and integer. Okay, we'll just say that, okay, we'll just have a precondition that the degree can't be negative. Or what? What else? How can I build this from in that data type? I can add two polynomials together. Yeah? Or I can multiply two polynomials together. That's the data type for this. Okay, so how do I represent this in my data? Well, this is a polynomial, which is the addition of two terms, or it's the addition of two terms, the addition between a term and another polynomial, which is the addition of two terms. So this term is going to be 3x squared, term 2x, and term 1, 0. Yeah, because it's the constant term. Okay, so we'll do this. There's f. Oh, I need to derive show. Deriving show. I don't know why it shows up in magenta if it's not the thing. Okay, so there's f. Okay, so I need to define a function derivative. And I want a derivative should take polynomials to polynomials. Now, what did I say is the only thing that we have to do to define functions over data? Make sure that we've defined one pattern for each pattern in the data. How many patterns are there in the data? There are 3 patterns, okay? Let's just go through it one by one. What does it mean to take the derivative of a term with this coefficient and this degree? It's the term c times d, d minus 1, right? That is the sort of derivative of this is 6x. Yeah. Okay, what's the derivative of if I add two polynomials together? Yeah, it's just add the derivative of f with the derivative of g. What does it mean to take the derivative of the product of two polynomials? Yeah, so I'm just going to say we'll just do this. F prime is the derivative of f, g prime is the derivative of g. Where that's, and I'm, okay, so what is the derivative here? So I'll just remind you of this. F g prime is equal to f prime g plus g prime f. Yeah, product rule. So here's product rule. Let's add the multiplication of f prime and g with the multiplication of f and g prime. Okay. Here's f. There's the derivative of f. So I just did like what all of undergraduate, the differential part of undergraduate calculus in like 5 minutes. I didn't even need 10 minutes. Yeah. It's still multiplied by 0. It's not technically mathematically incorrect. I'm not saying that there's like not problems intrinsic to how we've implemented this, but it's not wrong.
Then it would be wrong.
We change the last term to 3-0?
F.
No, because you still multiply by 0 when it comes down. Okay, so this is actually one of the questions on your homework is to define simplification. So I'm going to give you something like a polynomial with a bunch of like mods. Well, I'm going to give you a polynomial with multiplications, and I'm going to say, write me the function that removes the multiplications, switches them with adds. And then you're going to write another function that simplifies that. But all it's going to require you do is define patterns, is just define a bunch of declarative patterns to make it work. There's no processing. Haskell's all just pattern matching. Okay, so I'll give you back the remaining 3 minutes. I was going to do integral calculus next, but I guess I just won't, right? I can't do integral calculus, right? 2 minutes will do all of integral calculus. Okay, bye, chat. I'll have another assignment deployed on Friday. Yeah. Bye, chat. Bye, chat.